Hello, everyone. Good afternoon, all of you. So we'll start with today's quote by Steve Jobs. He says, "Your work is going to fill a large part of your life, and the only way to be truly satisfied is to do what you believe is great work. Then you will have the satisfaction that I'm doing a great work. And the only way to do great work is to love what you do. So when you have passion, you are going to do great work. If you haven't found it yet, keep looking and don't settle. As with all matters of the heart, you will know when you find it." So great quote by Steve Jobs, the great Steve Jobs. And okay, yesterday we missed this. Yesterday is the birthday of Yuri Gagarin. Do you remember who is this?
Yes, sir.
Who he is?
First man to space.
First man to rocket space.
Yeah, first man into space. Okay, first man into space. Okay, and today is the birthday of Fitch. He is a Nobel laureate in physics, and he is one of the bold and great scientists who could contradict the available science that is there at that time, which is accepted science. This is very tough thing for many of the scientists. Whenever you come or do a revolutionary research which contradicts the existing theories that are believed, it's very difficult for survival to publish it. And you have to have a lot of confidence and courage. That's what happened to Galileo also. He found that the Earth moves around the sun, but till then, people believed that sun is at the center and Earth is at the center and sun is moving around. And when he came with this particular new reality, so he found it difficult to survive, and complete world is against him. Complete church is against him, right? Because they believed in heliocentric, and he's geocentric, and he's telling heliocentric theory. So actually, he suffered a lot during all of his life, and he's forced by the public and the government to say that what his theory is there, what he is telling the public is wrong. So he's forced to tell like that. Okay, so he's an American particle physicist, Nobel Prize winner for physics in 1980 for an experiment conducted in 1964 that disproved the long-held theory that particle interaction should be indifferent to the direction of time. So that was believed at that time, but his theory contradicted it. He had been the first to observe radiation from muonic atoms, that is, from species in which muon is orbiting a nucleus rather than electron. This work indicated that the sizes of atomic nuclei were smaller than that had been supposed to be. He went on to study kaons, and in 1964 began his research led to the discovery of violations of fundamental symmetry principles in the decay of neutral K-mesons. Okay, he completely worked in modern physics, and he is a very great scientist. So he says, at any one time, there is a natural tendency among physicists to believe that we already know the essential ingredients of a comprehensive theory. But each time a new frontier of observation is broached, we inevitably discover new phenomena which force us to modify substantially our previous conceptions. I believe this process to be unending. So it must be there. There must be evolution. There must be new theories. And because that shows that your understanding is more depth, and that the delights and challenges of unexpected discovery will continue always. That's what he says. Okay, today we discuss about cascade theory. And before going to that, we will see just because there is a large gap, we will just recollect what we have done for axial flow compressors. Okay, so we are doing this. So we have seen the advantages over centrifugal compressors, and we have seen the property variations across stator and rotor, and then we have discussed about the velocity triangles, and we have seen what is psi, phi, and r, and interrelation among them, and then we have discussed about non-dimensional velocity triangles, and then effect of reaction on blading and triangles. That is 0% reaction, 100% reaction, 50% reaction, like that. We have seen how the blading will be and what the effect on the velocity triangles. And then we have discussed about pressure ratio and factors affecting pressure ratio. And also we have discussed about work done factor. What else we have discussed about? What else we have discussed about? Yeah, actually 3D analysis, that is radial equilibrium theory. Right. And then various methods of designing we have seen, like free vortex design, first power design, and exponential design. Actually, there is another method of designing also we didn't discuss, which is called as constant reaction design. Okay, in this particular one, what happens is we assume constant reaction from up to tip. Okay, but this method will not satisfy radial equilibrium equation. Okay. Okay, remaining things calculations will be somewhat similar, because once you know a reaction and you know the already axial velocity and blade velocity at the mean blade, so you can get the other things from the other triangle, other radii. Okay, so these are the things I think we have discussed, and then we are discussing about design process. So in the design process, so we have to calculate the speed, annulus dimensions, such things, and then we have to get the pitch line design, right? That is at the main radius. and design along the blade, that is at up to tip. Okay, so then comes the blade design. Okay, so about this we are going to concentrate on today. So this needs understanding of cascade theory. Okay, so this is what we are going to discuss today. Okay, so this cascade we were discussing about that. There are two types. One is angular cascade, and another is rectilinear. Okay, straight rectilinear cascade. Okay, so angular cascade means you will have a rotor-like thing only, but it is stationary. So you will have blades on this. Okay, so this is angular cascade. Straight rectilinear cascade we have already discussed. Like this. This is a infinite number of so this is called as a 2D representation of 3D cascade. Okay, so and we have to do experiments on this. So you will have angular tunnel, and rectilinear cascade tunnel. Okay, so for each one we have this, and usually we prefer to have this particular rectilinear cascade tunnel, because angular cascade tunnel we have to do experiments on number of angular cascades with different up-tip ratios. So that's the problem with the angular cascade tunnel. So we prefer the rectilinear cascade tunnel. So we can see some of the figures. How will it be like that? Okay, and another thing is so a blade design. There are two things we require. So we need required blade deflection, which is epsilon, which is beta 1 minus beta 2. And the second one, required diffusion with optimum efficiency, or with minimum stagnation pressure losses. Okay, so because this is both stator and rotor or diffusers, right? So in the rotor and stator, which are diffusers, so we know that okay, the W is 0 and Q is 0. So H naught is constant and T naught is constant, and P naught is constant if no losses, and P naught decrease if there are losses. Okay, so entropy increase and P naught decrease if there are frictional losses. So that P naught delta P naught, that is the stagnation pressure loss, that should be minimum. So these are the two main requirements. Okay, so I have to measure, right? So the deflection and the delta P naught. So these are the two things are to be measured. And another thing is, this is another thing, like when you design blade, we are going to get blade angles. And blade angles, till now what I was telling is blade angles are approximately equal to relative velocity angles. This is approximately equal to, they are different. So what we do is we make a notation, right? Beta 1 and beta 2, these are relative velocity angles. And we'll put beta 1 prime, beta 2 prime. Dot are blade angles. Okay, but okay, there is a small notation difference from the book and to the way I am teaching, right? So when you take Cascade, Cascade is a stationary one, right? Cascade is stationary only, and so there is nothing like relative velocity, right? That's why he uses alpha 1 and alpha 2 for inlet angle and exit angle, and V1 and V2 for inlet velocity and exit velocity, right? So, but I will be using beta 1 and beta 2 because we are using beta 1 and beta 2 for relative velocity. I am using beta 1, beta 2. In the textbook, he uses alpha 1, alpha 2. Okay, so I thought there may be confusion like that. Just be careful about that. Okay, so that is one thing I wanted to tell about. Okay, and the choice of variables. So whenever you are doing a design, the variables are to be chosen either based on the designer's experience and also based on correlations from experimental results. Okay, so based on these two, we decide about the variables. And so these are the two types of wind tunnels we will have: annular tunnel and straight cascade tunnel. And so this is a straight cascade tunnel and this is the annular tunnel. So this is the way an annular cascade will be there, and there will be flow over this in this way. And here, this is the tunnel. Okay, I will show you the full tunnel later. And at the exit, there will be a rectilinear cascade will be there. And there will be a provision for changing the angle of incidence. Okay, I will show you a better figure for this 2D cascade test section. This is 3D cascade test section. Yeah, so this is the way we will have. And okay, this is the complete tunnel. Here I have, and there are two types of wind tunnels if you see. So they are classified as direct flow and recirculating flow. Okay, so this it is a very costly one, and if you want to have a fresh air, and if I don't want to have the air taken from the atmosphere, and if you want to recirculate the same air, so this is type of used, actually main preferred in water tunnels. That is recirculation, because I cannot purify water every time. Otherwise, everything gets spoiled because of the salts in the water. So usually in IISc Bangalore, we have a water tunnel, recirculating water tunnel. But wind tunnel, it's not a problem. Usually we will have direct flow tunnels. And here there will be two types. One is suction type. Another is blowing type. So I want to have an airflow in the tunnel. So there can be two ways we can get the airflow. Either you keep a fan at the entry and blow air. Okay. And this is blowing type. And suction type, have a fan at the exit and suck the air through it so that air flows. Okay. Okay, we have this type of tunnel in our lab. Suction type tunnel. We have a fan at the exit and it sucks the air. Okay, so blowing type, why we are having blowing type is because I have the cascade at the exit. So you cannot have both fan and the cascade at the same place. So cascade is kept at the exit and we blow air over that. Okay, so this type cascade tunnels are blowing type. Okay, so this is this type. So we have fan at the entry. Okay, if you want to have a body here, and if you want that the aerofoil or aircraft or automobile, such a model, if you want to keep and you want to study, then we will not have blowing type. We will have fan here and it sucks the air. If I have fan at the entry, what happens is the flow will get a lot of circulation and disturbance and all. I want a smooth parallel flow on the body. So that's why normally in the laboratories, wherever I know it's not a cascade tunnel, usually normal tunnels are suction type tunnels only. The cascade tunnel will be blowing type. Okay, and even if I have transonic tunnels and supersonic tunnels, they are all blowing type only, right? Maybe I can write that. So in transonic and supersonic tunnels, what we do is we store large air at large pressure and suddenly we release it at the entry. So it just goes with high velocity. I cannot have continuous supply of transonic flow or supersonic flow air, right? So it is an intermittent type. These two are. So I will have intermittent flow, okay? So I will have large stored air and suddenly released and till the air is over and it will go with transonic or supersonic velocity. And again we'll stop. And again we fill the reservoir with high pressure air and again you release it, blow it. So like that. Is everything clear?
Yes, sir.
Yeah. Okay, once or twice I will just ask and you respond. Otherwise, because everything is a calm class, right? Okay, this is the cascade tunnel. Here what we do is, this is the entry duct. And here fan or blower, because both are similar, which increases the pressure. Okay, and we have a conical diffuser, right? So that large area is covered like this. And because here I want to settling chamber, because as I told, when I have a blowing, so there will be a lot of circulation and eddies are mixed, and a lot of disturbance will be there. I want to make it settled. Okay, so this is called a settling chamber. And even those eddies are to be split into smaller one, and they have to die. Okay, so for that I have honeycomb chambers will be there, meshes or honeycomb chambers like things will be there, like small mesh. If air goes through those small mesh, those large eddies get split into smaller and smaller eddies, so number of meshes may be there. And again there will be another settling chamber, and then I have a contraction cone. Okay, this contraction cone is given because whenever I have favorable pressure gradient, I will have a nice flow coming out of it. Okay, so for that we will have a contraction cone. Okay, and if it is a normal tunnel, so there will be a constant area duct will be there here, which is called test section. But here, because I have a cascade, I will have a cascade here like this. Okay. So this cascade is kept and the flow is blown over that, and it takes the turning. And here I have to keep probes. So this is to find out what is the P01, okay, stagnation pressure at the entry. And I will have probes kept like this. Okay? So here there will be a traversing, you can have a probe which can be traversed. Okay, from this point to this point, I can move the probe and calculate how the things vary. And here also I can have traversing probe here. Okay, so there will be a slot kept here, and you can put the probe through that, and you can just move it along that, so that I can measure along the length. Okay, so that is that. And so here there is a turntable mechanism like this. Okay, this is this. On this I have the blades kept, so I can rotate this one. Okay, so that the angle of incidence can be changed. Okay, so when I rotate it, the angle of incidence can be changed for the cascade. Okay, so these are the things that are there, and I'll have the probes also. There are two types of probes. Okay, these are the yaw meters, they call this. We use pitot static tubes for measuring the total pressure, and then yaw meters, right? So these are to calculate velocity and the direction. Okay, so here what happens is I will have two holes here, or there are holes like this, so that I can find out. Actually, I have to find out stagnation pressure probe, suppose if you keep. Okay, so how to get exactly to the direction of the flow? So I will have two probes on either side, and if I get the stagnation pressure same on both, then it shows the direction of the flow. Okay, so that is I think it is explained here. The principle of operation is the same in both and consists of rotating the instrument about its axis until a balance of pressure from the two holes is obtained. So the bisector of the angle between the two holes then gives the air direction. Okay, that is the way we find out the direction of air. Okay, so we are going to calculate the measure P01, P02, and beta 1, beta 2, okay, B1, B2. The velocities and directions at the inlet and exit, and total pressure. Okay, so this total pressure loss P01 minus P02, this is represented as omega bar. This is total pressure loss. And non-dimensional total pressure loss, like omega bar by half rho V1 square. So this is called as pressure loss coefficient. Pressure loss coefficient. This also represents drag. Okay, and epsilon is beta 1 minus beta 2, which is deflection, which represents lift. Okay, so and do the measurements at various by varying incidence or I. Okay, so this is the way we have to do the experiments. And these experiments, as I told in previous class about aerofoil, like that, in the same way, if I have incidence here and lift force, we get like this, isn't it? So deflection also will come like this. And the total pressure loss coefficient Y, it is like drag. Okay, so it comes something like this. And so in between it will be like flat thing, and then it will increase like this. And this is the point of stalling. Okay, so this value here, it is called as epsilon s, stalling deflection. Okay, and so sometimes it is also a little bit flat will be there. I don't know exactly where it comes. And so there is another way of doing. If I find out this is y minimum, and if you take a point where the losses are 2 times y minimum, right? So this point corresponds to stalling point. Okay, that is double losses wherever you get. So their stalling deflection will come. And so when I design, it should not be near to that. It should be a little bit away from that, so that whenever incidence changes, all right, so it should be safe. There should not be stalling. So usually we will keep what is called as epsilon star. Okay, this is called as nominal deflection. And how much it is? It is 80% of stalling deflection. Okay, so this is the design point we'll keep. Okay, this is the safe deflection. It is better to design for that. Okay, so that is the way we do it. And this epsilon star is found to be a function of S by C and beta 2. So this is pitch chord ratio, and this is exit angle. Okay, so if you do experiments with different S by C pitch chord ratio, if you change and if you do the experiments, so I'm going to get this set of graphs for each type of pitch chord ratio. And if I can draw plots for that, with this, I will show you the Cascade results. Okay. So this is the way we get it. And epsilon star is 0.8 epsilon s, or epsilon s is 1.25 epsilon star. And this stalling loss is equal to 2 times y minimum. Okay. And so we are going to get curves like this. So here, for different S by C pitch chord ratios, if I do, I'm going to get for each beta 2, what is the epsilon star. So if I take that, I'm going to get graphs like this. I'll take beta 2 here and epsilon star here. So we are going to get so S by C is 1.5 and S by C 1.0, 1.5. So S is pitch and C is chord. Okay, here actually what we are doing the design, right? So at pitch line design, we got all the angles. Okay, so beta 2 is known and deflection is known. So I can find out what is the pitch chord ratio, optimum pitch chord ratio for that. Okay, so select S by C from the graph for the values of beta 2 and epsilon. Okay, so for these values, what is S by C? I have to choose from the graph. Okay, so once this graph you may not be having always. Okay, so this is given through correlation. This is called as Vogel's correlation. So whether you use the graph or use the correlation, you get almost the same S by C. Okay, so these graphs are represented by a relation like tan beta 1 star minus tan beta 2 star is equal to 1.55 by 1 plus 1.5 S by C. Okay, these Howell's correlations are very important and useful in blade design. This is one of the correlations. Another correlation we will discuss again later. Okay, so if I designed it, beta 1, beta 2 are known. So using beta 1 and beta 2, I can find out what is S by C. Okay, so obtain S by C from Howell's correlation. Okay, and in the first step, we have annulus dimensions are calculated in step 1, which gives me height of the blade, because h is equal to RT minus R hub, tip radius minus sub radius, which gives h. Okay, so here h by c is usually chosen approximately equal to 3. Okay, this is out of experience of many of the decades. So it is found that h by c of 3 is optimum. So once you calculate h from the annulus dimensions, and so this gives me c chord. And so S by C is already known here. So S is equal to S by C optimum into chord. So this gives me pitch. Okay, so once I know pitch, I can calculate the number of blades. Okay, so number of blades N is equal to 5dN by S. Okay, annulus dimensions already calculated. So tip diameter, hub diameter, mean diameter, all of the things are known. So knowing the pitch, I can find out the number of blades. So these calculations are to be repeated, right, for both rotor and stator. Stator and obtain N for stator. So this is NR. So NS for stator, number of blades for stator. Okay, so here one check is to be made. Okay, there should not be common multiples between NR and NS. Why? Because to avoid possibility of resonance. So there will be harmonics, right? And there should not be any match of that, and otherwise there will be resonance. So I have to choose properly NR and NS so that there will not be any common multiples. So there are two choices. So given number for NS and prime number for NR, or even number for NR and prime number for NS. Okay, so previously at the beginning, choice 1 is used, but now choice 2 is preferred. Why? Because if there is a damage of any rotor blade, right? That blade and opposite blade are removed without much balancing problem. Okay, so because they are even, so if one blade is damaged, normally people used to stop the whole thing and replace it and take it out and replace it and then again start it and all, and till you get the new blades. So there used to be a lot of break between the operations. But if it is even number, so when you take out the damaged blade and you take opposite one, so that there will not be much balancing problem. If just the one is removed, which is damaged, and if you want to try to run it, there will be balancing problem. But if it is even number, if you remove opposite blade and if you run it, there will not be much balancing problem. So people started taking even number for the rotor and time number for the stator. Okay, so this is the way it's chosen. Okay, this is HBC about 3 like that. So all these things we have discussed. So in the okay, the use of prime numbers for rotor blades is less common than used to be the case. This is a result of development in the mechanical design, which have resulted in the ability to replace damaged rotor blades in the field without need for rebalancing the rotor system. Okay, and now we will see some cascade nomenclature. Okay, so anyhow, C is the chord and S is the pitch. So pitch means the distance between the similar points of the on two successive blades. Okay, so if I have this like thing, so the distance between these two is the pitch, and if I draw a chord line, so the distance between the leading edge and trailing edge, this is chord, this is leading edge, this is trailing edge. So if you take any similar points here, and if you take the distance, it will be S. Okay, that is the pitch. So that's why pitch is equal to pi d by number of blades. Okay, so if you take the circular one, the distance between the blades is pi d by n. And okay, these are the things. And we have okay, V1 and V2, inlet and exit, air angles, and beta 1, beta 2, sorry, air velocities. and this is inlet and exit, air angles. Okay, and beta 1 prime, beta 2 prime, these are inlet and exit blade angles. Okay, and theta 1, theta 2, theta t, these are all camber angles. That is angle between chord line and velocity. Okay, and some more also we will discuss. Okay, and if I draw a line joining the leading edge and trailing edge, this is the chord line, and this is the axial direction at the inlet and exit, right? This is the tangential direction. The blade is going like this, and all angles are measured with respect to the axial direction. And this angle is called stagger angle. Lambda is called stagger angle. And so if I draw a mean line, this is called camber line or mean line. Okay, so if I draw the tangents at the inlet and the exit, okay, so angle between these two at the inlet is incidence. Oh, sorry, theta 1, sorry. Camber angle at the inlet, theta 1. And angle between these two is theta 2, camber angle at the exit. And if I extend these two, I told you about this. This is the total camber angle theta, which is equal to theta 1 plus theta 2. Okay, so that is if I draw a line like this top one is theta and bottom one is top one is theta 2 and bottom one is theta 1. So theta is equal to theta 1 plus theta 2. These are camber angles. And so this angle here, this is the blade angle, beta 1 prime, because this is the actual blade angle. And similarly, this is beta 2 prime, blade angle. And how these are related, if you see at the inlet, lambda is equal to beta 1 prime minus theta 1. And at the exit, lambda is equal to beta 2 prime plus theta 2. Right? And if I want the theta, the total camber is equal to theta 1 plus theta 2. Right? So theta 1 plus theta 2, what will you get from the previous, these two relations? I will get beta 1 prime minus beta 2 prime. This is the planned deflection. How much camber, how much angle I have given. So the air has to turn to that angle, right? If air angles and blade angles are same, this theta must be deflection. Okay, so I have given a bent or the curvature in such a way that it gets deflected by that angle. Okay, So this is beta 1 prime minus beta 2 prime. And now I am telling air angles are different to blade angles. The air enters with some angle of incidence. That is, instead of beta 1 prime, it goes with a different angle. So this I will take it as V1. It is the same, at this angle it is entering. With actually it has to go in this direction, but it is going in this direction. So this is angle of incidence. And so the angle of the velocity is beta 1. The air angle is beta 1. Everything with the axial direction. So beta 1 and beta 2 are air angles. And here I is equal to beta 1 minus beta 1 prime. It has to go through beta 1 prime, but because I have to give an angle of incidence to have the lift, so I give at a different angle, that is beta 1. So angle of incidence is beta 1 minus beta 1 prime. And the air has to go out with beta 2 prime angle, but what happens is there will be boundary layer developed over this. And because of the boundary layer, so what happens is instead of following the mean line, it goes a little bit away from here. It will not go this way, but it go along this way. So it deviates from the blade angle. So this is the angle of deviation, delta. This is incidence. And delta, which is beta 2 minus beta 2 prime, right? This is called as deviation. So this exit angle, this is beta 2. Any doubt you ask me, right? So this is the angle of deviation. Instead of going with beta 2 prime, it is deviating because of the boundary layer. So that angle of deviation is beta 2 minus beta 2 prime. And what is the angle of deflection? This is epsilon. Epsilon is beta 1 minus beta 2. It is entering at beta 1 and deflecting to beta 2. So the angle of deflection is beta 1 minus beta 2. Okay. And so here I will relate epsilon, I, delta, theta and all. So this what I will write it as beta 1 minus beta 1 prime plus beta 1 prime. I am adding and subtracting beta 1 prime. And here beta 2 is there. So minus of beta 2 minus beta 2 prime. I am adding here and minus beta 2 prime. Okay, so this is the way I can write. This is equal to beta 1 minus beta 1 prime is I. And beta 1 prime minus beta 2 prime is theta. Minus beta 2 minus beta 2 prime is delta. Okay, so epsilon is equal to theta plus I minus delta. Okay, this is an important relation. Epsilon is equal to theta plus I minus delta. Okay, so you have to understand all the angles: camber angle, stagger angle, theta 1, that is air angles beta 1, beta 2, and blade angles beta 1 prime, beta 2 prime. Okay, so theoretical deflection is camber beta 1 prime minus beta 2 prime. Actual deflection is epsilon beta 1 minus beta 2. And incidence is the difference between inlet angle and blade angle at the entry. And deviation is the difference between air angle and the blade angle at the exit. Okay, so all these angles we have to understand what actually each mean. So this epsilon is equal to theta plus I minus delta. So this equation holds good for both compressors and turbines. Okay, but I is equal to delta equal to those things will be a little bit different because the profile will be a little bit different, and so which are going to accelerate, or this is the decelerating, and there it is accelerates. So the relations will be a little bit different for theta I delta, but this overall relation between all these four, epsilon equal to theta plus I minus delta, holds good for both compressors and turbines. Okay, and so this is a nomenclature for these things. Okay, and I have to calculate them, right? So there is okay, I normally it is my choice, right? So how much incidence I wanted to give, and theta is also fixed. So delta is the value I have to calculate. So this, again, we have correlations, Powell's correlation for deviation. So this delta is given as m theta s by c whole power n. Okay, this is the correlation for delta, where m is equal to 0.23 2a by c whole square plus 0.02 beta 2. Okay, this is a correlation, that's all. Okay, and a is the distance of maximum camber point from leading edge, and beta 2 air angle or exit. Okay, air angle at exit, and here in degrees. Okay, normally degree we put in radians, right? But here in this relation, beta 2 must be in degrees, and this n is equal to half for compressors. Means delta is equal to m theta root s by c, and is equal to 1 for IGVs and turbines. That is delta is equal to m theta s by c. And this is the relation for compressors, and m is equal to, I think, 0.19 for turbines. Okay, so this is the way I have to calculate the deviation. And so if usually many of the for subsonic flows, camber line is chosen to be circular arc. That is, so camber line will be taken like this, and if I take the blade, it comes like this. So this is a circular arc. So if this is called, and if it is a circular arc, the point of maximum camber is this, and this is A. Okay, so for circular arcs, A is equal to C by 2, or 2A by C is equal to 1. Therefore, M becomes 0.23 2A by C whole square plus 0.02 beta 2. So like this it will be. Okay, and for high Mach number, we prefer parabolic arc. And A is to be calculated for this. And sometimes for transonic and supersonic compressors, we prefer double circular arc profiles. profiles with sharp leading edge and trailing edge. So it is something like this. Both are circular arcs. Are provided like this. Okay, so for transonic and supersonic compressors, but usually for subsonic compressors, we prefer circular arc. So usually, if you get problems, you are going to get circular arc profiles only. Okay, so once I calculate all the angles and how to draw the cascade. So it is something like I draw a line like this and draw a line with stagger. Draw a line with stagger. So because I know this line, at stagger angle, you draw this. And okay, so what I do is I will draw a line with theta 1 camber here. And also here I draw so with theta 2 just that. So here what I am going to do is I am going to draw this line, right? And I am going to draw this particular line because I know theta 1 and theta 2. These two lines I know. So I can find out the leading edge and trailing edge are known, right? So if I join them, I'm going to get the chord line. So that is the way we do it. Okay. I didn't draw the lower line. That's why it's the problem. Okay. So once I draw this and I draw this line and take the chord length on this along this, and here you draw the lower line. Okay. And now you draw a line with theta 1 and draw a line with theta 2 and extend this and extend this. So this is theta. And here you draw a circular arc, a parabolic arc, whatever it is, based on what is the type of camber line you want. So once I do that, so I got the mean line, I got the camber line. And here we take what is called as a base profile. There are a lot of base profiles are available from Göttingen, NASA profiles, and there are so many profiles are available in data books. So you have to choose one of the profile. And once you choose, it will be given like this. Thickness distribution will be given to you. So this is the way base profiles will be there. Okay, so at different, it is like I'll draw horizontally. This is the chord line. And at different values of, if I take x by c in this direction, so at different values of the x by c means actually it varies from 0 to 1. Okay, so at different values of chord, so I'll know thickness distribution, how much thickness it is. So that is the way I have to power impose thickness at different points, and I'm going to get a profile like this. Okay, so this is the way I draw the one of the aerofoil. Then go for a pitch distance. Okay. And again draw a chord line and do all these things so that you will get the another profile, and I'm going to get the cascade. So this is the way I can draw the cascade. So this base profile is to be chosen. So as I told, we have profiles by NASA, and we have profiles by GRKGupta. Okay, and many other sources are there. Okay, these are the main two organizations which provide the cascade data or aerofoil data like that. We have available profiles. So like that, we have to choose the profile. So in this way, we can calculate pitch, chord, and all the angles, and we can get the cascade. And once we get the cascade, we can fabricate it, and we have to take it to the tunnel, and we have to do the experiments. And from the experiments, we get the profiles. Okay, that is the variation of pressure loss or deflection and all those things we can get. We can get the so all these things we have to do. Okay, and then once I design this, I have to do the performance. Cascade performance. So that is, I have to calculate the lift and drag coefficients. So I'll quickly do this. So if I take in this way, and if it is coming with V1 here, is going with V2. And this is the average direction. This we call it as VM. And so here I have the profile here. Okay. And this is direction of VM. And if I take this, this is beta 1. This is beta 2. And this is beta n. Okay. And there will be two forces. One is the tangential force. If I take a point here, so there will be a force in this direction, axial force, and a force in this direction. This is tangential force. Okay, so this axial force comes due to the pressure difference between the inlet and the exit. So I have P1 here, here P2, P2 is greater than P1. So FA, the axial force, is because of the change in the pressure into the area between two blades, right? Because if I have like this, so this is S, between which the air is entering. So P2 minus P1 into S, and 1 unit distance perpendicular to the body if I take. So this is the axial force. And the tangential force is mass flow into CW2 minus CW1. So this is the tangential force. These are the two forces acting. But I am interested in lift and drag. And what are the lift and drag? The forces in the direction of flow and normal to the direction of flow. So the mean flow is in this direction. So I take L in this direction and drag in this direction. So I have to resolve the axial force and tangential force in the directions of lift and drag. Okay, and so if I draw this as the tangential direction, okay. Now FA is equal to P2 minus P1 into S. This I will write it as P02 minus half rho V2 square minus P01 minus half rho V1 square into S. Okay, so I already told P01 minus P02 is equal to W bar or omega bar. And I will write this as half rho into V1 square minus V2 square minus omega bar into S. Here also into S. And this can be written as half rho CA square. And this is, we are already written like this, secant square minus secant square beta 1 minus secant square beta 2 minus omega bar S, or half rho CA square into tan square beta 1 minus tan square beta 2 minus omega bar S, half rho CA square S. This is axial force. And if I take tangential force, mass flow is rho CA into S into 1. Okay, rho AV like that, rho and density into velocity into area. So density is this, and velocity perpendicular to the direction of this area is CA. So rho CAS into CW2 minus CW1. I will write this as VW1 minus VW2. So CA into tan beta 1 minus tan beta 2. That is rho CS square S into tan beta 1 minus tan beta 2. And this FA, I will a little bit modify. I will write it as rho CS square S. In tan square beta 1 minus tan square beta 2, I will write it as tan beta 1 plus tan beta 2 and tan beta 1 minus tan beta 2. Okay, so tan beta 1 minus tan beta 2. The tan beta 1 plus tan beta 2 by 2 is tan beta m into tan beta m minus omega bar S. Okay, so these are the two relations I have to use. This is tangential force and axial force. And I have to get L and D in terms of axial force and tangential force. That is rotation of the coordinate directions. So what will I get? L is equal to, and so because this is the direction, beta m, this is this. So this angle is beta m. So if I want a drag force, first I will write drag force. Drag force. So this is FA or FT sine beta m, because FT cos beta m goes into the direction of lift and FT sine beta m goes to the direction of drag. And for FA, because it is in this direction, and this is beta m. So it is FA cos beta m, but the direction goes opposite. Okay, because this is this way, so it goes the opposite direction of D. So FA cos beta, like this. And if I take lift force, I will get FT cos beta m plus FA sin beta. Like this I will get. And then I have to substitute this FT and FA into this. so that I will get the expressions for lift and drag. Okay, just I will take drag. So drag is equal to Ft sin beta m, this into sin beta m, minus Fa cos beta m, this into cos beta m. So here if you observe, so rho Ca square as tan beta 1 minus tan beta 2 is common here and here. If I take common both of them, so Ft cos beta m means, sorry, Ft sin beta m means this into sin beta m minus this into cos beta m. So cos beta m into tan beta m will become sin beta m. So this minus this means actually both of them gets cancelled. And I will be left with omega bar s only with this cos beta m, omega bar s cos beta m. Is this clear? Is this expression clear? This is Ft sin beta m, that is this Ft, this one into sin beta m minus this one into cos beta m. So here as rho a squares s tan beta 1 minus tan beta 2 tan beta m is there into cos beta m. What happens is this is sin beta m by cos beta m into cos beta m. It will become sin beta m only. So this expression and this expression gets cancelled and we will be left with only omega bar s and the cos beta m is there. So minus minus plus and it will become omega bar s cos beta m. This is one expression for drag. And when you take lift force, Ft cos beta m, so this into cos beta m. Again, I will take rho Ca square s tan beta 1 minus tan beta 2. If I take common, so Ft into cos beta m, this will become cos beta m minus, plus this second expression into tan beta m means sin beta m into tan beta m, sin beta m tan beta m minus omega bar s sin beta m. Like this it will become. So this cos beta m plus sin beta m tan beta m, can you tell me what it happens? Sin beta m into tan beta m becomes sin square beta m by cos beta m. So this becomes cos beta m plus tan beta m sin beta m. It will become cos beta m plus sin square beta m by cos beta m. If I take LCM, cos square beta m by plus sin square beta m by cos beta m. Like this it will become. Okay. So that is the way it happens to be. So rho Ca square s L is equal to rho Ca square s into tan beta 2, tan beta 1 minus tan beta 2 by cos beta m minus omega bar s sin beta m. This will become like this, and d is omega bar s cos beta. This is lift force and drag force. And then I want to find out CL and CD, which is equal to non-dimensional lift coefficient L by half rho Vm square C. CD is D by half rho Vm square C. Okay, so this I have to substitute and simplify. We will do in the next class. Maybe you are nearing to the next class. We will continue this in the next class. Any questions till now? Is it okay? You have to practice. Maybe when I'm doing everything, maybe look okay, but nothing you can remember, right? Unless you do it. Because one thing you remember, we are going to have offline exam. You have to remember and practice all the derivations and problems, right? So you cannot have an open book. So that is not allowed here, right? So you have to practice, and everything should be there. If you close your eyes, I have to see the expressions, right? So that is the way you have to be thorough enough. Okay, I will continue this in the next class. We'll quickly see some story.
Yes, sir.
So it is about J.K. Rowling. I think all of you know about her. Who is this?
Writer of Harry Potter.
Writer of Harry Potter, right? And now she is a big billionaire, right? One of the uh, almost in richness, but it's not so easy thing, right? J.K. Rowling did not have an easy ride on her way to the top. Right as she began writing and beginning work on the concept for the now ever famous Harry Potter book series, she became aware of the news that her mother had passed away. This news had sent Rowling into seemingly endless depth of depression, leaving her with little to no inspiration to continue working on her dream concept during this time, putting all her hopes and dreams on hold. Eventually, to try and recover from the news, she had moved temporarily to Portugal to teach English. However, after a failed relationship abroad, she had returned home and further trouble on her doorstep with a baby daughter as a single mother. And she was on unemployment benefits because whatever government a little bit give for unemployees. So with that, she used to survive with the daughter. And something which for many who have experienced it is string thin, very small amount, as well as mentally draining. It makes you feel like you are in bottomless pit. She had barely enough money to get her and her daughter by in life, and however, she would continue to work on her dream idea for Harry Potter whilst her daughter slept. When the baby was sleeping, she used to write. And J.K. Rowling would then go on to devote her life into the concept of her dream of Harry Potter, only for that idea to take 12 rejections from publishers over the years. So every year she used to go to different publishers and they used to reject her. So 12 rejections she has faced. See how hope she can have. This constant feed of rejection made Rowling feel like her concept that she had devoted her life's work was doomed to follow the same path she saw herself as, which was a failure. She is always thinking she is a failure, and the novels also, she thought they are a failure. Despite her numerous setbacks in life and numerous rejections of her dream idea, she found solace over time in doing what she loved, which was writing. This meant that she, despite how much she had been rejected and pushed down, would not give up, as this was her dream, and nothing was going to get in the way of her and getting her dream out of the world. And over time, she determined hard work would go on to bear fruit. Harry Potter as a book would go on to be published, and to this day, the series of books have grossed over $7.7 billion in revenue. This insane level of success would be what would cement J.K. Rowling's place as the first female billionaire author in history. As her book popularity grew more and more and showed no signs of slowing down, it then branched into an arguably even more successful series of movies. This was the stage of J.K. Rowling's life where all the trials and tribulations she had faced in her past, as well as her dedication to her craft, passion, and family, began to finally show. She had finally made it. Okay, what are the lessons? Setbacks are not to be wallowed in, they are to be learned from. And current situations are temporary, and you make them temporary. And social barriers and expectations do not determine your outcome. Okay, these are the various lessons we can learn. And she may look now like she had an easy ride on the way to success, but that is far from the case. A lifetime worth of challenging setbacks and rejection that she faced would have been enough to deter anybody from their dream and to give it to the seemingly endless loop of negativity and struggles. However, it did not deter her. It only drove her on in her path to becoming a female and literary icon whose ideas spawned the most successful book series and one of the most successful movie series of all time. Okay, thank you. Thank you very much. And she says, we have all got both light and dark inside us. What matters is the part we choose to act on. That's who we really are. And it is our choice that show what we truly are far more than our abilities. Okay, thank you very much. See you. We'll meet tomorrow at 8 o'clock.
Thank you, sir.
Thank you, sir.
Thank you,
Thank you.
sir.
Okay.
Excuse me, sir.
Yes, Dipanshu.
Sir, these days we are doing the CFD simulations, and sir, like in implicit scheme or the semi-implicit scheme,
Okay.
so coherent number the maximum number coherent number which we can take is because if I am taking coherent number greater than 1, I am getting the results with which